In this lecture, we are going to show the partitions of unity theorem. Indeed, we will use that our manifold admits an exhaustion by compact sets, and then some local arguments. So this is the statement of the theorem. Let M be a Hausdorff and paracompact zero manifold, but we can really assume that it is second countable. Consider an open cover of M. And then there exists a CR partition of unities subordinated to the cover. What we are going to consider is the case R equal to infinity, because there is really not much of a difference between that case and the finite differentiable case. And we are going to use the following fundamental lemma that we are going to assume that it is known. This is an analysis result, and that says the following: given positive real numbers a and b and a natural number, which is going to be just the dimension of the Euclidean space we're working in, there exists a C-infinity function eta from Rn to the closed interval such that eta is equal to 1 and the closed ball of center 0 and radius a, and it is equal to 0 outside of the open ball of center 0 and radius b. Okay, so we're going to be in a situation in which, if this is a and this is b, the function, it is going to be equal to 1 over here, and it's going to be equal to 0 over here. And of course, here we have a transition from 1 to 0. Okay? If we take a look to what this means in the real line, okay? Let's consider here 0, a minus a, b minus b. The function eta could be a function whose graph is something like the following. Sorry. Something like this. Okay? And it is not difficult to find such function. So let's assume the fundamental lemma from now on. Okay, we want to find a partition of unity subordinated to an upper cover. And in our definition, the functions, the theta i's, have supports contained in ui. Let's go into relax a little bit the definition. What we claim is that it suffices to show the existence of a family of CR functions, but we are going to work with C infinity, theta j, such that the family of the supports is locally finite, exactly as it has to be. But now, instead of assuming that the support of theta j is actually contained in uj, we are going to suppose that it is contained in some of the elements of the open cover. Okay? That happens for every index, and indeed we are changing the index set because let's remind ourselves that the open cover was actually indexed by lambda, okay? And moreover, of course, we have to require that the sum of these functions is equal to 1. So the unique difference is that now we are considering that the supports are not necessarily contained in uj, but they can be contained in any element of the open cover. And if we have this, indeed, we are going to have a partition of unities subordinated to our open cover with the previous definition. Why is that? Okay, so consider now, given, okay, so fix a point I that belongs to lambda, right? And we're going to define fi as the set of indexes in gamma, okay, such that alpha of j is equal to I, right? What we get, actually, what we can do is defining alpha sub I. Okay, well, alpha is not a good idea because alpha was already used, but maybe gamma sub I as the sum of the data sub j's where j belongs to fi. This is well defined because the support of the data functions is a locally finite family, and so this kind of sum is always well defined. Okay, very good. And what happens is that since this family of supports is locally finite, we have something that it is very cool, and it is that the support of gamma I is the union of the support of the theta j's, where j belongs to fi. In general, this is not true. If you consider a sum of functions, for instance, a series, the support could change. But since we are here on the locally finite case, this holds. And because of that, what we get is that the family of the supports of the gamma I is also locally finite. Okay? But by construction, these supports of the gamma I are indeed contained in ui. And of course, the sum of the gamma i's is the sum, okay, here is the sum of the theta j's, and this is equal to 1. So in this way, we got a family of functions, gamma I, okay, such that this family of functions satisfy that the supports are a locally finite family, the support of every gamma I is contained in ui for every I in lambda, and the sum of these functions, which are all non-negative, is equal to 1. So this proves the claim. We just need to show this result over here, okay? We can actually consider this reduction. Let us continue the proof. Consider an exhaustion by compact sets of M. We have, by definition of exhaustion, that Kj is contained in the interior of Kj plus 1 for every j. And we have that M is the union of K1, K2 minus the interior of K1, K3 minus the interior of K2, and so on. Okay? If we make a very, very simple picture, okay, this would be K1, K2, K3, and the first set is this one, second is this, sorry, this closed annulus, the third one is this another closed annulus, and so on. right? And we actually want to give the functions that appear in the partitions of unity theorem. Let's see how we can actually do that. Okay, so we have our manifold M as a union of these sets. Let us consider one of them. For instance, let us consider the set k, j plus 1 minus the interior of kj. This is a compact set because it is a closed subset of a compact set. So it's compact. And now we are going to consider a point in this set. And what we want is building a C-infinity map that it is equal to 1 in a small neighborhood of X, and whose support is contained in one of the sets of the open cover. Okay, so we fix this point X, and there exists a local chart, okay, phi sub X from UX to BX, okay, whose domain contain X, and we can assume, for instance, that the image of the point X is going to be 0. Yeah, just because it makes our life a little bit simpler, nothing fancier. So what happens is that if epsilon, if a positive real number is actually small enough, then we have that the closed ball of center 0 and radius epsilon is going to be contained in B sub X, okay? And okay, let's keep these facts. So we're working with kj plus 1 minus the interior of kj, and in particular with one point in there, right? And we are considering a local chart that sends X to 0. So we're assuming that for some epsilon, which is going to be small enough, the closed ball of center 0 and radius epsilon is contained in Bx, okay? And we want a little bit more. We're going to consider the preimage of this closed ball. We are going to require actually that this is contained in the interior of kj plus 2 minus k sub j minus 1, okay? In order to keep consistency with the notations, let's consider, yeah, like this. This is possible because this set over here is open and it contains the point X. So since this is actually going a base of neighborhoods of the point X, for some small epsilon, this thing happens. So this happens actually for a small epsilon. For small positive epsilon, and the same thing happens with the first condition, right? And of course, we can require that this preimage over here of the closed ball of center 0 and radius epsilon is contained in one of the open sets of the cover, right? For some I. Again, it's because X is contained in one of them, and this is describing a base of open neighborhoods of a base of neighborhoods, not open, but a base of neighborhoods of the point X. So we can consider epsilon that satisfies all these properties, right? What we can actually consider now, it's a function rho that it is going to be C infinity from Rm to R to indeed to 0, 1, where small m is the dimension of our manifold, and that is given by the fundamental lemma. We are going to require, for instance, that the restriction of rho to the ball of center 0 and radius epsilon divided by 2 is equal to 1, and that rho restricted to the complementary of the ball of center 0 and radius epsilon is equal to 0. And then what we're going to do is considering the function, the composition of rho and phi sub x. A priori, this function is just defined in ux, and it goes to 0, 1, and of course it's infinity, right? But we have to realize that because of the way we are actually defining it, okay, the support of this function is indeed a compact subset of ux, right? And so we can extend this function to the whole M by defining the function as equal to 0 in the points that do not belong to ux, right? So we define sigma x as the composition of these two functions. Here it should be rho x, right? And okay, and this function is indeed a C infinity function from M to the closed interval 0, 1. Right. And it satisfies, of course, as we said, that the support of sigma sub x is contained in ux, but it is also contained in ui, so that's very, very, very good for us. And indeed, the support is also contained in k j plus 2 because of this property over here, minus, indeed minus, minus, well, indeed it's in the interior, it's doesn't matter very much. The interior of kj plus 2 minus kj minus 1. It is contained in all these sets. Okay. Now, let's recall that by definition, sigma x applied to x is actually equal to 1, right? So we can consider now the sets of the form, the sets of points in which the value, the function, sigma x has positive values. For x in kj plus 1 minus the interior of kj. This is a compact set. And obviously, since x belongs to this set, we deduce that this union contains the compact set kj plus 1 minus the interior of kj, right? Since we are actually considered an open cover of a compact set, there exists indeed a finite subcover. So there exist points x1, x2, xk such that the union of sigma sub x sub j greater than 0 contains kj plus 1. Well, here maybe we should use a different letter, sub L from L from 1 to k, and here we have the situation. Okay. Yes, that's what we have. And indeed, now we are going to keep all these functions, right? So for K1, we are going to have a family of functions built this way. I don't know. And it's going to be finite, okay? It's going to be a finite family. And what we are actually seeing is that they have several properties. All of these functions, the support is okay. The support is contained in indeed in an element of the open cover, and it's always contained in K2, for instance, right? And moreover, what we have is that the sum of these functions is positive in K1, right? What happens when we consider K2 minus the intersection of K1? There we are going to have, again, a family of functions, again, a finite family. The supports of these functions are contained, all of them, in K3, okay? And the sum of these functions, okay, is positive in K2 minus the intersection of K1. What happens, we're going to do one more. If we consider K3 minus the intersection of K2, we have here, again, a family of functions. The support is going to be contained in K4 minus, I think, minus K1. And the sum of these functions is positive in K3 minus the intersection of K2, and so on. So what we're going to get is, first of all, a family of functions that it is going to be countable, because for every j, we are getting finitely many functions, and the countable union of finite sets is countable. The supports of all these functions are contained in some set of our open cover. That's good. And if you have any point of the manifold, there exists one of these functions that is positive on this point. For instance, if x belongs to K1, there is one of these of the functions in the first set that is positive in x. If x belongs to K2 minus the intersection, the interior, sorry, of K1, one of these functions is going to be positive at x. If x belongs to this set, one of these functions is going to be positive at x, and so on. So we have a family of functions, a countable family, such that for every point, at least one of these functions is positive at this point. But we have more, as that this family of functions is locally finite, because from the third set on, we have that the supports are disjoint from K1. From the fourth set on, all the supports are disjoint from K2. From the fifth set on, all the supports are disjoint from K3. And so that implies that if we consider here our list of functions, and let's going to consider them in a sequence. Let's going to renumber them. What happens is that what we saw is that the set of natural numbers such that the support of sigma sub j intersection with KL is non-empty, this set is finite for every L, for every natural number by construction. And that implies, in particular, that the family of the supports of the sigma j's is actually locally finite. So this is almost already a partition of unity. The unique thing that it is not clear, because we can consider the sum of these functions, okay, and we already know that it's going to be positive. We know that the sum from j equal 1 to infinity of sigma j is going to be positive for every point of our manifold. And again, this sum is well defined because the family of supports is locally finite. But now it is very easy to build the partition of unity, because we just need to consider gamma j as sigma j divided by the sum. Okay, let's use a different letter, right? The supports of sigma j and gamma j are the same. Of course, it's well defined because this function in the denominator is never zero. And it is clear that by construction, the sum of the gamma j's from j equal 1 to infinity is equal to 1. So this satisfies all the properties that we needed to show the partitions of unity theorem. The partitions of unity theorem is one of the most important and consequential results in differential topology because it is used to globalize local results. Indeed, we will see an application in next lecture. We are going to show that any manifold that is Hausdorff and paracompact admits a differentiable proper function. Thank you for your attention.